Linearization is one of the toughest topics you're going to see in honors physics. So I want to take a moment to talk about what are the first things you should think about and sort of try to understand some of the theoretical side of this, which I think is the most important. So the first question you should ask yourself, in my opinion, when you see some nonlinear data, is what's the most basic relationship between the two variables? What I mean by that is, as the one variable increases, what happens to the other one? Does it decrease, stay the same, or increase? So please take a second, pause the video, see what you think for each of these three relationships at the top. Okay, so as B is going up, A is going down. That's pretty interesting. In the second one, as D goes up, so does C, and likewise, as F goes up, so do E. So the second and the third graphs are kind of similar. The first one is in its own category. So let's go ahead and think about what do you do when the answer to that question is one goes up and the other goes down, as in the case for A and B. Let me redraw A and B here just by itself. Okay, so as B goes up, A goes down. As we know, one of the tools that we have for linearizing is squaring one of either the independent or the dependent variable. But I'm going to argue that that's not going to be helpful. So if you square a set of numbers, so let's say we have real simple numbers, and we square them all, you can see that if these numbers were increasing before they were squared, they're still going to be increasing afterwards. And the same as if it was decreasing. So if we had a decreasing data set and squared, it's still going to decrease. So if we want a line, we need to have both A and B be increasing together. And so squaring will not be helpful to us. What is helpful to us is if we do some kind of an inverse function. So that's going to take an increasing data set and turn it decreasing, or vice versa. Although mathematically we could do it either way, we could take the inverse of A versus B, or the inverse of B versus A. It comes out nicer, and you really should do the inverse of the independent. So we're going to do a 1 over B transformation. So if we make a new plot, which is 1 over B versus A, then that should turn, if it's just simple inverse data, into a line. And so again, I think this is fairly obvious from the fact that as one of our original variables was increasing, the other was decreasing, which means we need some kind of an inverse function to make it linear. So then the next question is, what happens if as one increases, so does the other, as in our second or third case? So let's take a second and think about that. Okay, so I redrew our two second graphs on the right. As we discussed before, both of these graphs, as one increases, so does the other. So how do we figure out what to do next? I think the second question that I would consider asking is, as the one variable increases, how does the other variable increase? There's a couple tools we can use to help us answer this question. The first one, and probably most common, is called a tangent. And a tangent is basically the slope of a graph at a particular point. And so practically how you figure out the tangent is you pick a point, and then you draw the line that touches that point on the curve, but it doesn't cross it. And it's a little messy on the computer here, but here are a couple tangents. And then you can look at the slope of the tangent line to tell how quickly C is changing for a constant increase in D. So here you can see that the lines are getting more steep over time. So the second tangent here is steeper than the first one. That tells us that for a constant increase in D, C is increasing by larger and larger amounts. Another way to figure this out is something I call rise over run triangles. And if you're going to do a rise over run triangle, it's real important that you keep a constant run. So you just pick some arbitrary run. I'll pick this amount, and then you see how much the rise is. So I have this much run, and then I have that much rise, and then I do kind of the same thing somewhere else. So let's say if I continue this on a bit, and I need to go over the same amount of run, and then I see how much rise it is. You can see it's going to be off the computer screen. And so again, you can see for a constant increase in D, C is getting larger by greater and greater amounts as that goes up. So as you know, if you square a number that's larger than 1, it's going to get even larger. And so if we were to square those vertical values, they're already getting really large for values out here where d is kind of large. Those things are just going to get way, way bigger. So we need to stretch this graph in the other direction. We need to pull it horizontally to the right. And so how we do that is we're going to square the independent. So this one here, this one that's going up by a constant amount. And so instead of increasing by a constant amount as it is right now, so here it's going up by the same as it went over there, if you square a number set, so let's say if we do x and x squared, so 1, 2, 3, I think you'll agree it's going up by a constant interval of 1 each time. But if you square those numbers, you can see that they're not going up by a constant amount anymore. Now they're going up by more and more. And that's what we want because the vertical is also already going up by more and more. And so this transformation to do it is going to look like a original graph of this guy. We're going to do a d squared transformation, which will become this guy. And then last but not least, let's think about the second graph I put over there. It's much the same story as the one we just did. So if we redraw that guy like this, then you can see here as f increases, so does e, so we know that they're both going together. We're not going to do an inverse transformation. But in this case, if we look at the slopes, or if we look at the rise over run triangle, so let's just do a constant run like that and look at the rise. If we do about the same run, that's really important. You can see that the rise for the same amount of increase in f, for larger value of f, was much less. So even though e is increasing, it's increasing by less and less amounts for a constant increase in f. And so that tells us that we're going to do just the opposite. We're going to have to square the vertical in this case to make them larger. And so if we do e squared transformation, then we're going to get something like this. And this is the basic idea, in my opinion, what the hardest part is. Once you have this, then you can go ahead and start writing your specific math model. For example, in this last one, it'd be something in the form of e squared is equal to m, the slope, times f plus the intercept value. And you can worry about sig figs and all those things. But conceptually, I think this is the hardest part.